Well, hello again, and welcome to part 7 of the Modo particles series. If, like some fanatical despot, you want to order your particles to march hither and thither, then you've come to the right place. In order to inflict this particle domination, we need a plan. First, we have to describe the path that they should take. This can be done by creating a curve and animating a locator along the curve. Next, we need to order the particles to follow the locator. We can do this by force, that is, by using a particle operator. We can compute the vector between the locator and each particle and apply a force in the appropriate direction using some simple vector maths, or math if you would prefer. Using a force rather than setting the velocity means that the system will play nicely with other forces such as turbulence and wind. It also means that any movement will reflect the mass of the particles. So let's get started. So my first challenge is to create a curve and animate a locator along it, something even I should be able to do. Let's bring up the modelling tools and create a curve. Really, for the purposes of this demonstration, it doesn't matter what shape the curve is. So that's a curve. Next we need a locator. Add item locators locator. And we're going to animate this locator along this curve. So select the locator and select the curve. And then in modifiers, we just need to use path position. And now the locator is attached to the curve. And if we open these up, we'll see that some extra stuff has been added in to connect these two things together. If we select the constraint, this allows us to move the locator along the curve. And I've accidentally changed the path offset there, so we'll put that back. So changing the path percentage animates the locator along the curve, and this is going to be the target for our particles. So I think what we'll do now is animate this using just some keyframes. So first of all, I'm going to change the number of frames to something quite large. Let's change it to 1,000, say. And then we'll set a keyframe at 0%, and then at, say, 500, we'll set 100%, and then at 1,000, we'll set it back to 0% again. So as I scrub the timeline, the locator will move along the curve and then back again. It's actually quite interesting to explore what's happened as a result of putting in this constraint. So let's put the mesh into the schematic view. You'll see that the mesh has been connected up to this matrix compose and also to the constraint. So if you were wanting to build these things up by hand rather than using the built-in tools, you could connect your mesh to a matrix compose and then connect that to this path constraint modifier and also wire in the mesh, and then the output goes into the locator. One thing to note about the matrix compose is it takes a number of matrix inputs. These inputs, you'll see, are fed in from the scale, rotation and position. It's important that these happen in this order, otherwise strange things can happen. What I'm going to do though is put these nodes into their own workspace in case I need to come back to them later, and just to keep things tidy. So let's create a new workspace. I'll call it path follow, for example. And then if I select all these objects, then right click, we can move nodes to workspace path follow, and we've got a fresh top level workspace. If we want to see what's in the path follow workspace, we can just click on the workspace menu and select the path follow workspace, and there we go. Actually makes life a lot easier if you split your work up into distinct lumps like this. Next we need to create some particles. Let's suppose that they are birds in a field and that something has startled them into flight. It's probably that large locator. So we need a new mesh, and we'll call that field. And while we're at it, let's rename the path mesh to path. Let's create our field. It's a very small field, I think. And we need to make this into a particle source. So let's use a surface emitter. And we need to connect the field geometry into the surface emitter. If we run the simulation, we're getting particles emitted from that surface. But that's not really very helpful because there's an infinite number of birds taking off here, so what we need to do is just emit them in one quick burst at the beginning of time. So let's adjust the emission rate. Let's go back to time 0. Set the emission rate at time 0 to something large, like 1,000, and then move forward in time to say 5, and we will key the emission rate there to 0. So we should get a burst of particles at the beginning of time, but after that we won't see any more being emitted. I think I might adjust the initial emission rate even higher. Let's go to 2,000. There, that's a nice body of birds taking off into the air. This next step is the key to the whole thing. We're going to add a particle operator, and this will enable us to control the particles. We need to be able to control the force on each particle on the basis of its position relative to the locator. So we need to add the force and position features into the particle operator. Let's add the particle operator, and we can add some features. Let's add position. We only need to read the position, and let's also add the force feature. Now I like to separate out the read-only fields because otherwise the diagrams tend to get rather cluttered. So let's separate that channel out, and let's get rid of the kill and trigger because we're not going to use those. So the force that we're going to apply will depend on the position of the particle and on the position of the locator. That means we're going to need to know where the locator is. So let's bring the locator into the scene. Now it's dragged along some of its innards with it. We don't need that. Let's get rid of that by removing the node. We have two positions, and we want to generate a vector which is in the direction from one of these to the other, and that's just a simple vector subtraction. So let's add a vector operation, subtract. We'll subtract the position of the particle from the position of the locator. But we've got a problem because the locator doesn't output an XYZ position, it outputs a matrix. We need to convert that matrix into a position. Well, that's easy enough to do if you know how. There is a matrix channel modifier which will let us do that. It's called matrix vector. It takes a matrix as input and it outputs a position. Now we can subtract the two. That will give us a force, or at least it will give us a vector from the locator to the particle. We want to apply that force to our particles. Let's see what happens if we try that. Whoa! There's something not quite right there. Well, the problem is that this force is much too big. So let's disconnect these, and we need to scale that force down a bit. So I'll add in another vector operator, which is the set length operator. We can adjust the size of our vectors using this operator. And let's put the length into the schematic as well, just to make it easier to get to. Let's scale down this force. 0.001, let's see how that works. Now that's not so bad. The particles are being attracted to the locator. As the locator moves along, the particles move along with it. What can happen is that you do this subtract the wrong way round and the particles get repulsed by the locator. That's not a problem. You can either just swap the arguments around, swap the A's for the B's, or you could put in a negative length in the set length function, and that would be equally effective and somewhat easier. Using forces can sometimes lead to some rather wild and erratic behaviour. Supposing I change the force magnitude to 0.01 rather than 0.001. The particles are now a lot more lively and start getting out of control before too long. One way of damping down that sort of behaviour is to use the drag force in the particle simulation. So let's add a drag force of, let's say, 0.1. See if that helps. Well, it's not quite so lively, but I think we need a bit more drag, so let's put that to 1. And now our particles are behaving a lot more sensibly, following the locator nice and neatly. But it's beginning to look rather predictable. So one way that we can introduce a bit more randomness is to use some other forces. Let's add in a turbulence force. This should add in a bit more randomness to the behaviour of the particles. But because we've got that damping in place, they don't go completely crazy. Another thing that we can add in is this flocking operator. Flocking is probably not the right word for this, because what it really does is it controls the clumpiness of the simulation. Essentially, it tries to group the particles together into lumps controlled by a minimum distance and a maximum distance. So let's see what that does just out of the box. You can see, I think, that we've now got lumpiness in the way that the flocking is taking place. And we can control the lumpiness by adjusting these distances. If I change the minimum distance up, then the groups will be less tight. And you can play with that to your heart's content to get different sorts of behaviours. The number of particles in the neighbourhood search also controls how big the clumps are. We're on the home straight now. I'd like to add a replicator to the scene so that we can add some geometry. But first let's hide away all of these nodes into another workspace. I'll call the workspace flocking. And if I select all these nodes and move them into the flocking workspace, we can have a fresh workspace to play with. So let's move the particle simulation into our fresh workspace, and then I'd like to add a replicator. So add item particles replicator, add selected, and we'll use the particle simulation to feed the replicator. What shall I use as my prototype? Well, we need to add a prototype piece of geometry. Well, while you weren't looking, I sneakily added this bird prototype, which looks uncannily like a cone. And now we should have some prototypes following our flock. Now, immediately something is apparent. These birds are all pointing in the same direction, upwards. And that's not really how we'd expect them to fly through the scene. We would rather expect them to fly sort of nose first through the scene. So we can fix that by adding a direction constraint based off of the velocity of the particles. We'll need to add another particle operator, and to that particle operator we need to add some features. We need to add the velocity, which we're going to read, and we need to add the rotation, MNOPQR, rotation. Let's split off these read-only channels, move them over. I'm sorry, I spend an awful lot of time gardening these diagrams. So what we want to do is use this velocity to control the rotation of our prototypes. Well, we can't connect an XYZ velocity directly into a matrix rotation, so we need some way of affecting that. So we need to add a directional constraint, which is the thing that's going to arrange for our particles to point in the right direction, and connect that up to our rotation. And we need to add the velocity in as a position into the directional constraint. We don't need to set the from, because you can think of a vector as being a position relative to the origin. So we'll leave the from as the origin, and we'll feed this vector into the position 2. But again, we've got a problem because this is an XYZ vector and we need a matrix. Fortunately, there is a matrix operation for doing that for us. Matrix construct. We'll be constructing a position matrix. We can either construct scale or position. Well, position's what we want. We'll feed the X, Y, and Z in, and we should get a position matrix popping out, which you can plug into the direction constraint. And now our particles should be constrained by that velocity, but I anticipate trouble. Okay, so they are being affected by the velocity, but the direction they're pointing is not quite right. So let's look at the direction constraint, and the reason is that we've got the wrong axis. If we select the y-axis instead, then our particles are now pointing in the direction of the velocity. And that's more or less it. I think that's everything I wanted to show you in this video. I hope it was useful. Thanks for watching, and I'll see you in the next video.